All right, so we're going to go ahead and talk about our first type of sampling, and that is a simple random sample. Right, a simple random sample is a subset of a statistical population in which each member of the subset has an equal probability of being chosen. A simple random sample is meant to be an unbiased representation of the group. Right, so let's digest that bullet point for a second there, right? So let's say hypothetically I wanted to go and get the heights of our class, right? We all took a survey, we all reported our heights in inches, and let's say our class was not 25 students or 22 students, but it was 2,000 students, right? And it would be impossible for me to go ahead and let's say I didn't survey you all. Let's say I actually went and measured everybody, right? That would take a lot of time, that would take a lot of resources, and it's probably not feasible. So what I decided to do is then a simple random sample, and where I go ahead and I kind of essentially just pick names out of a hat. Now, if I took, let's say hypothetically, all of the nutrition majors didn't have their names in the hat, they were excluded for some reason, and then I picked out, and I then can't generalize the results back to that population, right? Because the nutrition majors did not have a chance of being included in there. Or on the same note, if PE majors, somehow there was some sort of error and then PE majors got their names put into the hat 2 times, then those are all things that can go ahead and kind of skew or disrupt a random sample, right? So everybody has to have an equal chance to be selected, right? So let's come back. Let's say there's 20 students in our class. Each student has the same probability that they can get in 1 out of 20, right? 1 out of 20 is my odds that is the percentage that I'm going to go in, and everybody has that same percentage, right? So let's go to this next bullet point here. A simple random sample takes a small random portion of the entire population to represent the entire data set, where each member has an equal probability of being chosen, right? Again, that equal probability portion again, and it's the same thing. We take a small random portion of the population, right, to go ahead and try to represent the entire population, or to try to extrapolate out, or to get a sample of the population and hope that it is representative, right? So researchers can create a simple random sample using methods like lotteries or random drawers, right? Okay. So a sampling error can occur when a simple random sample does not end up accurately reflecting the population it is supposed to represent. So let's say we had gone through some technical sampling issues, but let's say by chance we happen to oversample more PE majors than dietetics majors, right? Then we might not be able to go ahead and extrapolate. Or if the underlying population that you set is very, very disparate or diverse, right? Let's say we weren't made up of just PE and nutrition majors. Let's say we had earth science majors, and we had biology majors, and we had mathematics majors mixed in. We might not, and then they ended up in our sample, right? If we had a few of those students and then they ended up in our sample, they might skew our distribution one way or another, right? Or if, let's say, there was a couple of student athletes who played on the basketball team and they were very, very tall, and then they ended up being selected, they may throw off our sample too. But for the most part, if you have a well-defined population, then it should be normally distributed, which we will go ahead and talk through a little bit more coming up, right? So the next type of sampling is systematic sampling, right? So this is where we follow a simple system of selection, like every 10th person, right? Or so let's say hypothetically we select every second person that shows up to class each and every day, and then they become part of our sample, right? Like we do this because sometimes it's just easier or it just makes more sense, right? If we come back to our New York Giants football situation, hypothetical, if every fifth person that comes into the stadium gets selected, right, like there's a protocol that can be done uh, fairly straightforward, right? So systematic sampling is a type of probability sampling method in which members of a larger population are selected according to a random starting point with a fixed periodic interval. This interval can be called a sampling interval. It is calculated by dividing the population size by the desired sample size. And so let's also think about another systematic sample, right? I'll use a kind of a public safety example. Let's talk about motor vehicle checkpoints, right? Where you're driving down a road, everybody stops, and they might do something like every third car or every red car or, or every 10th car, something along those lines, right? The fixed periodic interval is called the sampling interval. It's calculated by dividing population size by the desired sample size. So let's say, we had 100 individuals that we were interested in, and we decided to sample 10, right? It would be 10 divided by 100, and then so it would be every 10th, we would then go ahead, every 10th participant would then be sampled, right? That's the sampling interval right there. Advantages of this methodology includes eliminating the phenomenon of clustered selection and low probability of contaminating data, right? So remember in the basketball example, in the classroom example, where if we had a couple of student athletes that played basketball, and if we all of a sudden were interested in the heights of this class, but then we ended up selecting that cluster, right? That cluster ended up like 3 or 4 basketball players ended up in our sample. They may skew the data, right? Over time, and when we go ahead and kind of talk about the central limit theorem, it really doesn't matter. But in one specific sample, it could skew your distribution, right? By doing a systematic sample, you reduce that bias by a lot, right? And then disadvantages include over or underrepresentation of a particular pattern and a greater risk of data manipulation, right? So less worried about the data manipulation part, but let's talk about this over or underrepresentation. Let's toggle back to our stadium example. Let's say hypothetically you always go ahead and we're only going to pick everybody who sits at the end rows, right? Every person who's in the end row or end seat of a section is who we're going to go ahead and select. Well, what if there's particular types of people who really prefer those types of seats, right? That's kind of like the thought process that you want to go through here with kind of over or under representation in a data set. Okay, so that is a systematic sampling. And then now what we're going to go and talk about is stratified sample, right? Now stratified sample is going to make a lot of sense once we kind of go over this. It's when we divide a population into groups by characteristics such as age or occupation or gender, right? So let's think back to our survey that we took. What are some of the stratas that we surveyed in response to, right? Well, major is one of them, right? Whether you're, nutrition and exercise science, you're dietitian, or you're a PE major, right? These are stratas that you can go. We can do age or age groups, right? Individuals that are 18 to 25, 25 to 30, 30 to 35, right? Et cetera, et cetera. Your gender, right? And what happens is, what we do is we create a strata, and then we then sample from the strata, right? So stratified random sampling is a method that involves the division of population into smaller subgroups known as strata. In a simplified random sampling or stratification, the strata are formed based off of the members' shared attributes or characteristics, such as income, educational attainment, right? So, you're trying to form, like, why do we use statistics, right? We use statistics to try to go ahead and answer questions. We try to make, statistic informed or data informed decisions when we go ahead and make a process, right? Stratified sampling is really the first step in kind of drilling down and getting a little bit more nitty gritty, right? Look, there are differences when it comes to majors, right? PE majors and dietetic majors. There are going to be differences. Well, what are the differences, right? How do you figure that out? Well, you figure that out by going ahead and paying attention to that and then stratifying. So then you create two groups. So now what we do with our data set is, rather than looking at a class as a whole, we split the class up into nutrition, exercise science, and PE folks in one side, and then exercise science and PE folks into one group, and then nutrition and dietetics into another group. And now let's go ahead and look at central tendencies and measures of dispersion, right? And let's see how the groups then differ from there. Stratified random sampling allows researchers to obtain a sample population that best represents the entire population that's being studied, right? Because we get to go ahead and kind of look at subgroups from there. So stratified sampling involves statistical inference using a subset of a population, right? So again, just trying to tell you what stratified sampling is in a kind of a different way. So hopefully, if one bullet point didn't resonate with you, this bullet point would, right? So stratified random sampling is done by dividing the entire population into homogeneous groups called a strata. So we use stratification, what was the other term? Stratification, stratified random sampling. These are all synonyms, right? These are all groups for essentially taking a population and then splitting them up into smaller populations based off of similar characteristics. The last bullet point here, stratified random sampling differs from simple random sampling, which involves random selection of data from the entire population, right? So simple random sampling, everybody is in there. Everybody has an equal chance. Stratified means that we have a subgroup that we're then going ahead and pulling it from. So I hope that is clear. Let's go ahead. And now we're going to go ahead and talk about cluster sampling, right? So cluster sampling is a two-step procedure. And so the very first thing that we need to go ahead and do is define the population that we're interested in, right? And we talked about that a little bit earlier. And then we separate them into different clusters. And then we choose clusters to go ahead for our analysis, right? So I think the easiest way to go through this one is by an example, okay? So let's say we're interested in 7th graders in the current school year in New York City public schools who eat breakfast, right? Like, do they eat breakfast or not? So step one, first you have to go ahead and you want to really clearly define the population you wish to study, right? So we're going to go ahead and say the population is children in the 7th grade that attended a New York City public school system in 2022. And if you take a look at this visual right here, you see, look, this is our universe of 7th graders, right? And it's not all 7th graders, right? There's no public school 7th graders here. There's no 7th graders from Long Island, or there's no 7th graders from Westchester here. Only in New York City 7th graders, okay? And in the school year 2022. So now, step two, what you want to go ahead and do is divide your sample into clusters, right? And ideally, you want your clusters to meet the following criteria. Each cluster's population should be diverse as possible. You want every potential characteristic of the entire population to be represented in each cluster. Each cluster should have a similar distribution as the distribution of the population as a whole, right? So let's digest those 2 points right over here. If we looked at the sample, right? If we looked at New York City school children that are in the 7th grade, right? You know, their age is going to go and range from, I think they're like 12-year-olds, right? So like young 12-year-olds to older 12-year-olds, maybe some 13-year-olds, maybe some 11-year-olds, right? Like that's probably going to rearrange. We want that diverse spectrum. We don't want only kids that were born exactly on the same day, right? So we want an age variability. We want to go ahead and look at, well, how many males and how many females are in this whole population, right? So it's probably going to be 50-50. So you don't want a cluster that has, 80% male and 20% female, right? When we talk about race ethnicity, I think this is going to be a good example. What is the population of 7th graders that are black, that are Hispanic, that are Asian, that are white, that are Middle Eastern, right? Whatever it is for that whole population, we want that to show in each one of the clusters that we then go ahead and create, right? Taken together, the cluster should cover the entire population. Therefore, so if you have 100 students and then you're going to create an equal number of clusters, and when you add up all of the clusters, it should be 100. So it would be something like 10 students, 10 clusters equals 100, right? And then, so what we're going to do is we're going to cluster the 7th graders by the school that they attend. And in order to cover the whole population, then we need every school in the city, right? You have to go ahead and make sure that there's no overlap too. So this is really important, right? We can't have one student, like a student has to be assigned to a cluster, a student can't be assigned to 2 different clusters. So keep that in mind right over there. Step 3, then what you do is remember now, so what we did was we took all the 7th graders and now we're clustering them by the school that they attend, right? So there is a PS 159 cluster, a PS 499 cluster, et cetera, et cetera. Although they should probably be ISs, right? So, IS 25, IS 34, intermediate school for you non-educators out there. And then so now you have all of your clusters, right? For each cluster, then what you're going to go ahead and do is draw those names out of a hat, right? And that's going to be your sample. So now you're not sampling on individuals anymore. What you're doing is you're sampling on the cluster itself. And when you sample on the cluster itself, remember each one is representative of the population as a whole, right? So this way you should really go ahead and get a very well diverse representative sample. And so if each cluster is itself a mini representation of the larger population, random sampling, selecting from the sample cluster, allows you to imitate simple random sampling, which in turn supports the validity of your results, right? So fact is this. If we took all the 7th graders and we randomly sampled, our population would look a certain way. By doing a cluster sampling method, it's going to mirror that, right? It's going to go ahead and mirror the simple random sampling. But the fact is that you took that extra step to create these clusters. It makes it that much more stronger and it makes it that much better, right? And a lot of times you would do a cluster because it just makes sense, right? It just makes sense to then be able to go ahead and sample by schools or by whichever groupings that makes sense to you. Okay, so that's going to wrap up this portion of the lecture, and then we will go ahead and I'll see you all soon for the next portion where we talk about sampling distribution and the central limit theorem. Bye, everyone.